In this video, we'll go ahead and calculate delta G for a reaction from tables of data, and this is going to be fairly involved, so stay tuned. So the reaction we're going to look at is 4 ammonias reacting with 5 oxygens and making 4 nitric oxides, or nitrogen monoxide if you prefer, and 6 waters. And I got to be a little bit careful with the state symbols here because the state symbols will vary. So sometimes I can find water in the liquid phase and the gas phase and the solid phase in my tables of data. So I got to make sure I know exactly which one I'm looking at. And we're going to do it at 2 different temperatures, 25 and say 125 degrees C. All right, I got to give you a table of data here. So I'm going to go ahead and write out underneath as neatly as I can each one of these 4 substances. And I'm going to give you the standard enthalpy of formation. And instead of writing those units out all the time, I'll just go ahead and divide them out, kilojoules per mole. And I will give you the third law of molar entropy. So that'll be in units of joules per mole Kelvin. And I'll just kind of speed this up so we get this table pretty pronto. Phew, that was fast. Okay, so let's calculate delta H of reactions. Because remember, to calculate delta G, right, I need delta H minus T delta S. So I can go ahead and switch to blue. So delta H of reaction is the sum of the heats of formation for products minus reactants. So what do I have here? I've got 4 NOs. So I got 4 NOs that are 91.3 apiece. I've got 6 waters, so that is 6 times by minus 241.8. The negatives here will get you. Minus my reactants, I got 4 ammonia, so I got 4 times by minus 45.9. Again, watch for the double negatives. And I've got 5 oxygens. And notice that heats of formation of elements are always 0 because it doesn't cost any energy to make a stable form of an element from the stable form of an element. And if I do all of that, I get minus 902.0. What are my units? I've been kind of sloppy here. I'm going to put kilojoules here. I'm going to assume that it's per mole up here, and I'm going to interpret all of these as numbers of moles. So when I multiply moles by kilojoules per mole, I'm left with kilojoules. Again, there is a little bit of disagreement in the community as to the proper way to handle that. So I'm just going to go ahead and leave off the moles if that's okay. Your textbook may disagree. Same thing with entropy, so I can use the third law of values. Notice that entropies of elements are no longer 0. So I've got 4 NOs, so I take 4 times my NO's value to 10.8. And I take 6 waters. Notice these gases, right, have massive amounts of entropy. And I do the same thing for reactants, but now I'm subtracting. So I've got 4 times 192.8, so the ammonias, and 5 times by my oxygen value of 205.2. And before I do anything here, I might want to go ahead and make a prediction. So I can see that I make 6 moles of gas on the right, and I make that from 5 moles of gas on the left. So I'm increasing my number of moles of gas by 1, so that normally increases the entropy. So oftentimes on the exam, right, I will ask questions like, hey, do you think this reaction leads to an increase or decrease or no change in entropy? And whenever you've got an increase in gas molecules, you can almost always be sure that the entropy goes up. And in fact, if I do this calculation, I get positive, so that's a good sign, 178.8 joules per Kelvin. The moles cancel out. So again, because the number of moles of gas increased, in this case, it went up by 1, that tells us normally the entropy will increase. All right, so we're at 25 degrees C, so let's calculate delta G. So delta G at 25 degrees C is delta H minus T delta S. And again, those are all standard states, I suppose. Standard conditions, I should say. So let me see. My units here are kilojoules, and the other one is joules. So I got to make sure I'm consistent. So let me go for both of them to be kilojoules. So minus 902.0 kilojoules minus the temperature. So 25 is 298 Kelvin, 0.15 if you want to be technical, times by delta S. So 178.8 joules is 0.1788 because I just divide by 1,000 kilojoules per Kelvin. So the Kelvin cancel out. Boink, and I'm left with kilojoules and kilojoules. So I can add, or in this case, I can subtract kilojoules from kilojoules. I get minus 955.5 kilojoules. So was that spontaneous? The answer is yes, it is spontaneous, because all you got to do is get delta G to be negative, and your universe's entropy goes up. And yeah, so that reaction can indeed happen at 25. So maybe you can pause the video and stop and calculate it at 125 degrees and see if you get the same thing. Is it spontaneous or not? Okay, pause, have a go. All right, so if you're back at 125 degrees C, I won't do this calculation, but hopefully you've done it. I get minus 973.2 kilojoules. So yes, it is still spontaneous. In fact, it is even more spontaneous than before, right? So it has even more of a driving force behind it. So that's pretty awesome.